Morning, everyone. Yeah. Okay. In today's section, we will continue what we started about the molecular geometry. From the beginning of these chapters, we talk about what? Chemical what? Chemical bonding, right?
Yes.
So we talk about the covalent, the ionic, and the metallic, and we know that the bond. This how actually the different element or different atoms bonded together. Today's actually we will talk about some kind of different bond, but it's not a chemical bond. We could name it a physical bond. This is intermolecular forces, IMF, intermolecular forces. This is mean it's not a bond, actual bond between the atoms. It happens a kind of interactions that happens beneath the molecules, between the molecules. Okay, so I want you to start these sections with this main idea. We are not talking about an actual bond. This is a physical bond, or simply, as we name it here, intermolecular forces. What are the intermolecular forces? The force of attractions between molecules are known as intermolecular forces. So it's a force of attractions between the molecules. The boiling point of a liquid is a good measure of the intermolecular forces between its molecules. This is mean how we could measure the strength of intermolecular forces by the boiling point. If we have a substance with high boiling point, this is mean high or low intermolecular attraction? High intermolecular attraction. So this is how we measure the strength or how we measure the effect of the intermolecular forces by boiling or melting point. Here, the strongest of the forces between the molecule, intermolecular forces vary in the strength but are generally weaker than the bond between the atoms. If we compare the chemical bond with intermolecular forces, actually there is no comparisons. For example, any types, the strongest intermolecular bond is called hydrogen bond. We will explain it. It's actually represent like 5% of the strength of the covalent bond, not even the ionic bond. This is mean there is no comparisons between the strengths of the chemical bond and the intermolecular forces. But how this is actually will make a crucial effect in the properties of the matter, like they affect the boiling point of the matters, and we will see that how that happens. In this sections, I will start to explain every single intermolecular forces, and we give some example of it, and then we get back to the slide. So the intermolecular forces vary in strength but are generally weaker than the bond between the atom, as we mentioned. Boiling point of ionic compound and melting tends to be much higher than those of the molecular substances. Forces between the molecules are weaker than between the atoms or ions. And you could see that the huge difference between the ionic compound and the covalent compound. As you see, the ionic compound, like potassium chloride, sodium chloride, calcium fluoride, all of them have high boiling and melting point because the electrostatic attraction of the ionic bond is very high. As we mentioned before, the ionic bond, one of the strongest bond, right? And we have here the molecular compound. It doesn't matter what type of intermolecular forces between them, but as you see that they are actually much lower than their boiling and boiling much lower than the ionic compound. Because the idea of measuring, we measure the intermolecular forces by what, guys? By their boiling point. Very good, Yanis. Okay. The strongest intermolecular forces exist between polar molecules. So, in each type of intermolecular forces, guys, we will classify what type of molecules this intermolecular attractions happen between them. Let's start by first intermolecular forces is called the dipole. Okay, dipole force. Because of their uneven charge distribution, anyone could remember me what did the polarity mean? Ali? Uneven distribution of a charge that create a partial charge upon the atoms. Partial negative upon the high or the low electronegativity atoms. Partial negative upon the atom with high electronegativity. Partial positive with the low electronegativity. Okay, so the directions of the dipole is formed dipole's positive pole and a negative pole. So a dipole is represented by an arrow with its head pointing toward the negative pole and the crossed tail at the positive pole. Because this is represented that we said that the polarity comes from the chlorine atoms have high electronegativity, ability to pull the electrons of the electron chemical bond toward this, and this is make a pole or a dipole. And the dipole this make two poles or two electrodes as we see. So let's explain it. The first type is called dipole force. Dipole force. Yeah. Dipole. Yeah, I will explain here. First, what's mean di? Two, right? And poles mean different poles, like the batteries of like the battery, positive and negative, right? But here in that case, so first, it's happened in what type of molecule? Polar or beneath polar molecules. Okay, guys? For example, if we have HCl, anise, which is one have high electronegativity, chlorine. Okay, so the chlorine attracted the electrons in the covalent of the bond toward them, and this is we make a dipole that represent the vector of the forces, the direction of the pole forces toward the chlorine atom. And this is make the chlorine, the hydrochloric acid here is a polar compound by forming what type of a charge upon the atoms? So above the hydrogen we put partial what? Partial positive above the hydrogen, partial negative upon the chlorine. And this compound here is a polar covalent compound, right? We name this, guys, what? We name this molecules dipole, right? Why dipole? Because it's two poles, guys, positive and negative. But it's not a complete positive, not complete negative, it's partial. It's not like the electrostatic of the ions interactions between the ionic compound. Yes?
Why we put the positive charge in front of H and the negative charge in Cl?
Because chlorine is the highest electronegativity. So this is electrons is of the covalent bond positive toward this make more electron cloud upon the chlorine, and this is partial negative. Yeah. And this is will make the other side of the molecules partial positive because of the low electronegativity. Small line? Yeah, the small line represented the positivity of this side. Okay? It's like this. Okay? It's like this, right? But we represent it as a vectors of force. Do you study the vector and force in physics, right? Okay. Remember this because we need this information. Now we need to explain dipole force. Okay? Dipole force happen in which type of molecules? Polar molecules. So it's non-polar molecules do not have dipole force. Okay? But we said that it's dipole force. And this is only one dipole, right? So where is the other dipole, guys? In any molecules, we know that in a because we have a tons of molecules, right? This molecule in continuous rapid motion, right? Depends on their states of matter, right? So if we have another molecule of hydrochloric acid near to it, like this, and these molecules here have also a partial positive charge upon the hydrogen, partial negative charge upon the chlorine. And if these two molecules come near to each other in a short distance, what happens between the opposite charge, guys? Attractions. And we represented the intermolecular forces by a dashed line, and we named this type of force of attraction dipole force. So the molecules must be in this sequence because the opposite charge, because the molecules are always in motion, right? And the intermolecular forces were represented by a dashed line. It happens between the atoms or between molecules. That's why we name it intermolecular forces, right? So this is the first type, dipole force. The second type, guys, is actually, it's a type of dipole force, but in some resources they make it like 3 times. It's called the hydrogen bond. The what? The hydrogen bond. So the hydrogen bond, so do you understand the dipole first? Okay. Why this is, my questions here, why this affect the boiling point of the metals. When we boil some metals, guys, we make what? If we have some water to boil, we raise the temperature of it, right? So that's why the intermolecular forces is the cause of rising some boiling point of some molecules, because I need some energy to break this intermolecular attraction, right? To break any bond, I need energy, and this is intermolecular forces. I need to separate them, so I need to apply more energy of them. That's why the boiling point of some substances here is rising. Okay? Second type of intermolecular forces is called hydrogen bond. It's called what? From its name, you could estimate that it's happened between hydrogen and a specific type of atom. Hydrogen and? Okay, these atoms here, for example, hydrogen and fluorine. Okay? Hydrogen and oxygen. And finally, hydrogen and nitrogen.
Only these three?
Yeah, only these three examples that you have to study in these sections. You don't have any more. The first example that we will take about the hydrogen bond, and I want you to predict the position of the intermolecular attractions. Okay? So, here we will take a hydrofluoric acid as an example, HF, of the hydrogen bond. I will draw the molecules like this. Right. It doesn't matter, guys. I could draw the molecules like this. Okay? So I could draw it like this. Or I just draw it like this because it's in continuous rapid motion, right? Because this is a molecule, it's a three-dimensional that moving in all directions. Okay, guys? My questions here. The hydrogen bond also happens in polar or non-polar molecules? Polar molecules. Must be polar molecules, okay? And we have here, this is only the certain example. Could anyone, and our condition here, the molecules must be in short distance, okay? If they are far away from each other, they could not actually get in contact, guys, and make an intermolecular attraction. Here, could anyone tell me where exactly I supposed to put the intermolecular attraction? The dashed line? Yes, Hamza. Where? Here? Because we said that it's beneath the molecules. It's not beneath the atom. So this is the intermolecular attraction here. Here is the intermolecular attraction. Here is the intermolecular attraction. And we name this bond here. What, guys? Hydrogen bond. Here, we will continue the hydrogen bond. The first example we take between what and what? Between what and what? H and F. Now, H and O in the water molecules. In what? In a water molecules. If we draw the water molecules, guys, we know that the water molecules is oxygen atom attached to covalently with two hydrogen atoms. What is the shape of water molecules? Bent, yes. And how many lone pair? Huh? No lone pair? Here. This would. One or two? Two, as Hazem said. It's two lone pair, guys. The lowest structures. And the shape is bent. Okay? Three atoms molecule. Bent. Because the lone pair is stretched and more in the molecular geometry. And the angle between the two hydrogen atoms here is what? 104.5, if you remember. This is what we take in the two sessions before. So if I draw an oxygen atoms, guys, this is the oxygen, this is the hydrogen. We know that the intermolecular happens between the molecules or happens between the atoms? Between the molecules. Yes, ya Ali. Okay? As you see, guys, we said that it's between O and H in different molecules. So this is molecule of water here, and this is a molecule of water. The hydrogen come near to the oxygen in a shorter distance and make a hydrogen bond. And make what? a hydrogen bond. So this is called what? Bond. Okay, yes? A type of dipole-dipole, yes? But we make it separate because, guys, if we compare the strengths of dipole-dipole and hydrogen bond is stronger than the dipole-dipole force. But in general, dipole-dipole is the strongest intermolecular forces, but hydrogen is stronger than dipole-dipole, yes.
Can you repeat what happened between the molecules?
There is, when they come in a short distance, we know that it's a polar molecule, guys. So there is partial negative, partial positive, partial negative, partial positive, right? So the attractions between the partial positive charge and partial negative charge in a short distance between oxygen and hydrogen forming a hydrogen bond type of intermolecular attraction. So the hydrogen bond also happens in what type of molecules? Polar molecules, yes. Another example for the hydrogen bond to understand it, yes. NH3, ammonia. Between the N and the H in ammonia molecule. The chemical formula, NH3. The shape of it? Anyone remember?
Yes.
What?
1 and 3 in the triangle.
Trigonal pyramidal عشان اللون pads that except. Okay? Yeah, one lone pair. Ammonia. Okay. Again, is it a polar or a non-polar? Polar, a partial negative charge, partial positive charge, partial negative charge, partial positive charge. Here, partial negative, partial positive. And the attractions, when they come in a short distance between them, the nitrogen will attract it to the hydrogen. The nitrogen will attract it to the hydrogen as what you find here. We name this type of bond hydrogen bond. Is it a chemical bond or intermolecular attraction?
No.
It's intermolecular attraction. Do you understand this, guys? So again, from the beginning, we talk about the dipole-dipole force. We said that any polar compound will have a dipole of a partial negative and partial negative positive charge. When these two molecules in a beaker, whatever it is, the molecules have tons of them, right? Millions of them. These molecules, when they are in continuous motion, when they move, it comes in this sequence in a short distance, there is electrostatic happens here, attractions between the partial positive, partial negative charge to form the dipole-dipole force. The hydrogen bond is a type of dipole-dipole force, but we classify because it's strongest dipole-dipole force. And you could see that it's happened between hydrogen and a certain atom. That's why we name it hydrogen bond. Hydrogen was fluorine, hydrogen was oxygen, hydrogen was nitrogen. First, we take hydrogen and fluorine in the hydrofluoric acid, and you could see that the hydrogen and fluorine, when they come in the partial, this is fluorine atom, have a partial negative charge. Here is the hydrogen have a partial positive, partial negative, partial positive, partial negative, partial positive. So electrostatic, when they come in a short distance, they make a kind of attractions between them. We name this intermolecular attraction. What type? Hydrogen bond. Both of them happens in the polar molecules. Yes, sir. LDF, London dispersion force or Van der Waals force. This is the third type, number 3, of intermolecular attraction. Van der Waals or Van der Waals. Okay? It's happened, guys. The example that he gave it to you here, it happens between what? The monoatomic atoms, right?
Yes.
The example he gave it to you for the helium atom, right? Helium atom. How did that happen? I want you to go to the book page 185. Look at the figure 5.13. Okay? Temporary. Very good. If we have a helium atom, this helium atom here have a nucleus. I have 2 of them. This is one is the weakest intermolecular attraction. Okay? Also, it happens in all the molecules, polar and non-polar. It happens in what? In all molecules, even it's polar or non-polar. So even the polar molecules have a London dispersion force. How this London dispersion force happen? Here we have an helium atom, the monoatomic atoms. Most of them have the London dispersion force. The London dispersion, as I mentioned, is the weakest, and we will know why. If you remember the structure of the atom, guys, what inside the atom? What? Nucleus. And this is nucleus contain what?
Proton.
Protons and neutrons. So what important for us? The protons. Here we take the helium. So the helium have two proton, right? Two proton, right? Inside the nucleus, right? Okay. Is the electrons in continuous motion or not around the atoms? Yes? Right? The electron is actually in continuous moving around the atom in the electron cloud in their orbital, right? Okay, we said that it's a momentary dipole. What I mean, if you look down here, it's a momentary dipole in the one helium atom. What I mean by momentary? This is mean if we just make freeze to the electrons while it's moving in a certain position at a certain moment, at a certain time, the electron actually is shifted to a side of the atoms. And here, the neighbor atom, because the attractions will happen between the atom and its neighbor atom. Okay? How will that happen? This atom also have like shift their electron in that position, and we freeze the atom. Imagine that we could happen. This moment here, guys, what is the probability to happen? Very rare to happen, right? Very rare to happen, right? Like in we know that the electron is actually moving with high speed in all the in directions and in the electron cloud, but could we just imagine that this has happened in a very little moment, right? This moment here will not last for a long time, right? When the electron shifted in a side of an atom, they make a momentary dipole. What I mean a momentary dipole? It means that it will form a partial negative charge on the side of the electron shifted and partial positive charge for the side that actually for the proton that not have any electron in this side. Remember, we talk about a moment when the electron actually shift, okay, to this direction. So what happened? They will attract, the proton here will try to attract to each other, and the electron here of the neighbor atom will attract here. And this is force here, we name it London dispersion force. Because of the low probability to happen, that's why it's the weakest actually. Because imagine that if you look to the book here, guys, the momentary dipole is one of the helium atom, and the dipole induced in the neighbor atom. Weak attraction force, London dispersion force, weak attraction. Or induced dipole. This is London dispersion. Happen in which type of atom? In all type of atom. What this type of bond, guys? Between what? The molecules. You see that? We know that the ice crystal actually hexagonal shape. You see the hexagonal shape, guys? Okay. Okay. This is the hydrogen. This is the London dispersion. So even noble gases, atoms, and the non-polar molecules can experience weak intermolecular attraction in any atoms or molecules, polar and non-polar, that the electrons are in continuous motion. As a result, at any instant, the electron distributions may be uneven. Like the electron shift to a side of an atom, uneven, right? And this will form what, guys? A dipole. Partial positive, partial negative, right? But this dipole is permanent or momentary dipole. Momentary, right? That's why it is the weakest. So how much it will happen, actually? Low probability to happen. It's happen, and in some cases it have a crucial effect, but we will see that in a certain properties of atom. As a result, at any instant, electron distribution may be uneven. A momentary uneven charge can create a positive pole, one end of an atoms of a molecules, and a negative pole at the other. And this, according to it, will make an attractions, okay, between them, as we explain it here in the as we explain it here, this is momentary dipole will form in the atoms, and this is in induced dipole will make them attraction, and this is London dispersion force, the weakest attraction. Another thing, yes, the dipole or the vector of the dipole. You have to remember that if you compare, for example, the water molecules and the carbon dioxide, CO2, and water molecules, which is one is polar, which is one is non-polar.
H2O is polar.
Polar. This is one here is non-polar. Why? This is one polar. This is one non-polar. If we draw the geometrical shape of it, the carbon dioxide, what is the, if you remember, what is the, for the carbon dioxide? Let's draw it. Draw the carbon, and this is oxygen, right? Okay? Do I have any lone pair upon the central atom?
No.
So what is the shape of the molecule? Linear. Which is atom is the highest electronegativity? Oxygen. So if I wanted to represent the dipole, guys, what is the direction of it? Right?
Yes.
This is the direction of it. That's why the carbon dioxide molecule is non-polar, because the two vector of force, they are the same force because the same atom is the two sides, but opposite directions. What happens if I have two vector of force at the same force but in opposite direction?
No.
Zero, right? So the total momentum here is zero. This is why actually there is no partial positive and partial negative charge upon this molecule here, and it's what? It's a non-polar. So what type of intermolecular attraction is found between the carbon dioxide molecules? London dispersion. Does we have dipole here? Okay. Here, for example, for the water molecule, as we represent, the direction of the dipole is actually in that direction, right? And the total dipole we represent it in that direction, so that we have partial negative charge upon the hydrogen, upon the oxygen, partial positive up on the oxygen. Another two molecules to finish it, the PF3 and the NH3 for the ammonia. We know that this is one here, it's trigonal planar, right? The P was exact angle 120, right? So we have here the fluorine high electronegativity. So this is one is polar or non-polar, guys. We have three vectors here, non-polar, three vectors in the exact direction that cancel each other, and the total momentum is zero, so there is no polarity. But here in the NH3, we know there is a lone pair, and this is molecules here, what we name it. So there is a total attraction of dipole here, because the hydrogen, this is one of the dipoles, one of the dipoles, one of the dipoles, and this is will cause a polarity, and the ammonia here is a polar dipole force. What type of intermolecular attraction? Hydrogen bond, because it's between hydrogen and nitrogen. So in summaries, last thing. According to the type of molecule, so they have to determine. The hydrogen bond happens between hydrogen and certain atom. But the dipole happens in all the polar molecules. But for the hydrogen bond, as you see that I just mentioned a specific example like hydrogen and fluorine, hydrogen and nitrogen, hydrogen and oxygen.
So we write these three.
Yeah. London dispersion happens in all the molecules. For example, noble gas is one of them, the monoatomic atoms. If it's non-polar, so it have London dispersion, because we know that it's because of the shifting of the electron attractions between atoms and the neighbor atom. Okay? So this is in total. Do you have any questions, guys? Because what is the moment to this actually shifting happens for the atoms? We talk about a moment to happen, right? This is why we name it momentary dipole, right? Okay. Very rare to happen. Yeah. From the electronegativity difference that we take it in the previous semester. Electronegativity difference. Higher than 0.4, it's a non-polar covalent. Lower than 0.7. And if you have one atom with low electronegativity, one atom with high electronegativity, this is considered to be polar, and according to the momentum also, or the vector's force, or the dipole. Because carbon dioxide, if you see it, it's a non-polar. Okay?